Let's say you've just got a job here. Your job is to make the acoustics of this place work. An opera diva, a soprano, is practicing for a concert in a few days' time. And she finds that when she hits a note, which is the C, 2 octaves above middle C, there's an annoying reverberation in here. The boss says to you, your job is to kill that reverberation. What are you going to do? Get it right, your boss will be happy, the audience won't notice at all. But get it wrong, your boss will be unhappy, and even worse, you'll have an unhappy opera diva.
This problem is actually easy in terms of the physics and engineering. What we're going to do is use the very basic formula. C is equal to F times lambda. The speed of sound is equal to the frequency of sound times the wavelength of the sound. And of course this holds true not just for sound waves but for all waves in fluids, and of course for all waves of any kind. Now we're going to engineer some kind of quarter wavelength absorber to absorb the annoying reverberation at the frequency that the singer is singing at. Okay, so a quarter wavelength is going to be equal to 1/4 C on F. Now we know what C is. That's the speed of sound in air, 340 meters per second. So to figure out how thick our quarter wavelength absorber is, we just need to know what F is. The absorber material might be some kind of building material. It will be mounted around the walls of the concert hall. How thick is it going to be? It's just given straight away by this formula. The trick is to figure out F. And the problem is that F is given to us in terms of musical language. The singer's singing at a C that is 2 octaves above middle C. Well, what frequency is that? Well, we've got to figure that out by studying a little bit of music theory. So according to scientific pitch notation, the musical spectrum is divided up into octaves. That's the same term that the musicians use. An octave is a factor of 2 in frequency. So middle C, denoted C4, I'm not going to draw 4s for all the other notes, but C4 is the middle C on the middle of the piano keyboard. The C that the singer is singing at was C6. That is the note the singer had, so we want to figure out what is the frequency of C6. And in between C6 and C4 is C5. So we have a factor of 2, so C5 has a frequency which is half of C6, and C4 in turn has a frequency which is a quarter. Now the scientific pitch notation tells us that all these notes are calculated based on the A above middle C. So this A above middle C has the standard frequency of 440 Hertz. That's the A above middle C. So this is, remember, as a factor of 2, F on 4 to F on 2. Now, the octaves are divided up into what are called semitones, and basically the semitones have frequencies which are a fixed ratio of each other. In other words, each of the keys in the piano has a frequency which is a same ratio of the key below it as that key has of the key below it, and so on. So in between the A and the C here, we've got an A sharp. That would be one of the black keys on the piano. And then we've got an A sharp, and then we've got a B. And there's no sharp between a B and a C. So we're going to count the semitones. We've got one semitone here, another semitone there, and a third semitone there. Now let's fill in all the semitones so we can figure out how many semitones there are in the octave. That's that factor of 2. From C to C sharp is one semitone, then C sharp to D, Then D to D sharp is another semitone. Then we've got D sharp to E. Now another peculiarity of music, there's no sharp between the E and the flat, and the F, sorry. Between the E and the F there's no sharp, but then there is certainly an F sharp. There is a G and there is a G sharp. And then we get to the A. So let's count the semitones. There's one here, there's two, there's the third, there's another semitone, a semitone there, 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 and there. In total, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 semitones. Because this is a factor of 2, the ratio between this note and this note, this note and this note, any semitone is a ratio of 2 to the 1/12th power in frequency above the previous semitone. So now with this information we can start to calculate the F that we need to get. So we know the F is going to be based on this 440 Hertz. 440 Hertz, 440 reciprocal seconds. Now if we want to get from that A to this C5, we're going to multiply by 2 to the power of 1, 2, 3 twelfths. And to get from the C5 to the C6, which is where the soprano is singing at, we just have another factor of 2. And it turns out that this is 1046.5 Hertz. So now we can plug this into our formula to figure out the quarter wavelength that we're after. Lambda on 4 is equal to a quarter, the 340 meters per second, divided by the 1046.5 we had just figured out, and that will give us a result of 0.081 meters. So it turns out that our material that we're going to use around the concert hall wall is going to be about 8 centimeters, and that should do the job of absorbing this annoying frequency. A very lengthy excursion into musical theory, you might think, but sometimes in real life engineering that's just what you have to do. Go outside of engineering into some other area to get the number you need.